Discrete mathematics. Discrete mathematics deals with several select topics in mathematics that are essential to the study of many computer science areas. These topics, namely mathematical logic and proofs, are discussed in this unit. Mathematical logic. Logic deals with all types of reasoning. These reasonings may be legal arguments or mathematical proofs or conclusions in a scientific theory. Logic is widely used in many branches of sciences and social sciences. It is the theoretical basis for many areas of computer science such as digital logic circuit design, automata theory, and artificial intelligence. Logical statement or proposition. A statement or a proposition is a sentence which is either true or false, but not both. A sentence which is both true and false simultaneously is not a statement. Rather, it is paradox. Simple statements. A statement is said to be simple if it cannot be broken into two or more statements. All the statements in A and B are simple statements. Compound statements. If a statement is the combination of two or more simple statements, then it is a compound statement. Basic logical connectives. The words which combine simple statements to form compound statements are called connectives. We use the connectives and, or, etc. to form new statements by combining two or more statements. We use symbols shown above to denote conjunction and disjunction. Conjunction. If two simple statements P and Q are connected by a word and, then the resulting compound statement P and Q is called the conjunction of P and Q and is written in this form as shown above. Truth tables. A table shows the relation between truth values of a compound statement and the truth values of its substatements is called a truth table. A truth table consists of rows and columns. For the above problem, the initial columns are filled with the possible truth values of the substatement and the last column is filled with the truth values of the compound statement on the basis of the truth values of the substatement written in the initial column. If the compound statement is made up of n substatement, then its truth table will contain 2 to the power of n rows. So, in this problem, 2 power 2 is equal to 4 rows in the truth table of P and Q. Using A1 and A2, enter the truth values of P and Q in the final column based on the corresponding truth values of P and Q in the first two columns. The compound statement P or Q and R consists of three simple statements P, R and R. Therefore, these must be 2 power 3 is equal to 4 rows in the truth table of P or Q and R. The truth value of P remains the same value of T or F for each of 4 consecutive assignments at logical values. The truth values of Q remain at T or F for 2 assignments and that of R remains at T or F for 1 assignment. So, in the first 2 columns, enter T, TT, TF, T, FT, FT, FF, FF. In the third and fourth column, enter TT, FT, TF, TT, FT, TF, FF. So, in the final column, based on the corresponding truth values at R, P or Q is T, F, T, F, T, F, F, F. Last column. Logical equivalence. 2 compound statements A and B are simply logically equivalent or simply equivalent if they have identical last columns in their truth tables. In this case, we write A is equal to B. Conditional and biconditional statements. We frequently come across statements of the form if P then Q. Such statements are called conditional statements or implications. They are denoted by the symbol shown above, read as P implies A. The condition P implies Q is false only if P is true and Q is false. Accordingly, if P is false, then P implies Q is true regardless of the truth value of Q. Tautologies. A statement is said to be tautology if the last column of its truth table contains only T. That is, it is true for all logical possibilities. Groups. Given any non-empty set S, the possibility of combining 2 of its elements to get yet another element of S endows S with an algebraic structure. An empty set S together with a binary operation asterisk is called an algebraic structure. Group is the simplest of all algebraic structures. It is one operational algebraic system. Definition: a non-empty set G together with an operation asterisk, that is G comma asterisk, is said to be a group if it satisfies the following axioms as shown above. Solution: from the Cayley's table, we see that all entries in the table are the members of G. So, the closure property is true. Multiplication is always associative. The identity element is 1 and it satisfies the identity axiom. The inverse of 1 is 1. The inverse of omega is omega squared. The inverse of omega squared is omega and it satisfies the inverse axiom also. Therefore, G, dot is a group. The commutative property is so true. G, dot is an abelian group. Since G is a finite set, G, dot is a finite abelian group. By computing the products of these matrices taken in pairs, we can form the multiplication table given below. 1. All the entries in the multiplication tables are members of G, so G is closed under. Therefore, closure axiom is true. 2. Matrix multiplication is always associative. Since the row headed by I coincides with the top row and the column headed by I coincides with the extreme left column, I is the identity element in G. 4. I dot I is equal to I, that is, I is the inverse of I. A dot A is equal to I, that is, A is the inverse of A. B dot B is equal to I, that is, B is the inverse of B. C dot C is equal to I, that is, C is the inverse of C. From the table, it is clear that dot is commutative. Therefore, G is an abelian group under matrix multiplication. Solution: 1. Closure axiom. From above, G is closed with respect to addition. 2. Associative axiom. Since the element of G are all real numbers, addition is associative. 3. Identity axiom. We have 0 plus x is equal to x. Therefore, 0 is the identity element of G and satisfies the identity axiom. 4. Inverse axiom. Therefore, minus a plus minus b root of 2 is the inverse of a plus b the root of 2 and satisfies the inverse axiom. Therefore, G is a group under addition. 5. Commutative axiom. Therefore, the commutative property is true. Therefore, G, plus is an abelian group. Since G is infinite, the G, asterisk is an infinite abelian group. Let G be the set of all rational numbers except 1 and asterisk be defined on G. A asterisk b is equal to a plus b minus ab for all. Solute: let G is equal to Q minus 1. Let a, b belongs to G. Then a and b are rational numbers and a not equal to 1, b not equal to 1. 1. Closure axiom. A asterisk b is equal to a plus b means ab is irrational. We have to prove that a asterisk b not equal to 1. On the contrary, assume that a asterisk b is equal to 1. Then a plus b minus a is equal to 1. That is, b is equal to 1. Therefore, a not equal to 1, 1 minus a not equal to 0. Therefore, a into b not equal to 1 and hence a into b belongs to G. Therefore, closure axiom is 2. Associative axiom. A into b into c the whole is equal to a into b the whole into c. A, b, c belongs to G. That is, E is equal to 0. Since A not equal to 1, that E is equal to 0 belongs to G. Therefore, identity axiom is satisfied. 4. Inverse axiom. Let A inverse be the inverse of A belongs to G. By the definition of inverse, A into A inverse is equal to E is equal to 0. By the definition of multiplication, A into A inverse equal to A plus A inverse minus A inverse. Therefore, inverse axiom is satisfied. Therefore, G comma asterisk is a group. 5. Commutative axiom. For any A comma B belonging to G, A into B is equal to A plus B minus B is equal to B plus A minus A is equal to B to A. Therefore, multiplication is commutative in G, and hence G comma asterisk is an abelian group. Since G is infinite, G comma asterisk is an infinite abelian group.
Find out which of the following sentences are statements and which are not. Justify your answers. Write down the truth value T or F, that is, true or false, of the following statements. Construct truth tables for the following statements. P or negation Q. Negation P or Q. P and Q or negation Q. P and Q or negation P and Q. P and Q negation R. Use the truth table to establish if the following statements are tautologies and which are contradictions. Negation P and Q. P and negation Q or negation P or Q. P and negation Q or negation P or Q. Show that P tends to Q equivalent. Negation P or Q. Show that P tends to Q and tends to P are not equivalent. Let S be a non-empty set and 0 be a binary operation on S defined by x or y is equal to x. Y is an element S. Determine whether 0 is commutative and associative. Show that the set of all positive even integers forms a set group under the usual addition and multiplication. Is it a monoid under each of the above operations? Prove that the matrices 1, 0, 0, 1, 0, 1, 0 form a group under matrix multiplication. Show that the set of M of complex number Z with the condition mod Z is equal to forms a group with respect to the operation of multiplication of complex numbers. Find the order of each element in the group. Z5 minus 0, minus 5. Show that G is equal to 2 raised to n by n belongs to Z is an abelian group under multiplication.
We have already dealt with random experiments which can be described by finite sample space. We have studied the alignment and computation probabilities of events. In the study of science, one often deals with variables as a quantity that may assume any one of a set of values. In statistics, we deal with quantity that may assume any one of a set of values. In statistics, we deal with random variables whose observed value is determined by chance. Random variable. The outcomes of an experiment are represented by a random variable if these outcomes are numerical or if real numbers can be assigned to them. For example, in a die rolling experiment, the corresponding random variable is represented by the set of outcomes 1, 2, 3, 4, 5, 6, while in coin toss experiment, the outcomes head, H, or tail, T, can be represented as a random variable by assuming 0 to T and 1 to H. In this sense, a random variable is a real valued function that maps the sample space into the real life. There are two types of random variables: discrete random variable and continuous random variable. Discrete random variable. If random variable takes only a finite